First, I would like to thank the Epoch Foundation organizers for the invitation. It is a great honor for me to be here and share with you some of my thoughts on the future of electronics. In the past 50 years, electronics have been mainly based on semiconductors with three-dimensional nature, such as silicon and compound semiconductors. Today, I will talk about a new type of electronics, two-dimensional electronics based on materials with only one atom thick. In 1959, Professor Feynman made a very famous speech called "There is plenty of room at the bottom." Feynman talked about the problem of manipulating and controlling things on a small scale. His talk is often regarded as the beginning of nanotechnology. It is really visionary because this speech was made even a few years earlier than Moore's law was proposed. Talking about small things, what would be the smallest engineered feature that you have at this moment? If you have a smartphone in your pocket, and if you are willing to really open it, you probably can find something with feature size like this. This is pretty small. If you take a look back at the electronics that were invented in the last century, the Moore's law not only holds for the last 6 decades, it actually worked pretty well for the last 120 years, if you count the number of calculations per second per dollar. This is achieved by a steady scaling down of the device size. Every time we find a way to engineer things at a smaller scale, we enable new applications that have never been imagined before. This game of scaling is particularly powerful for the development of transistors. Here shows the first transistor invented in 1947 at Bell Labs. After 7 decades, this is what we have today. It is called a FinFET, a fin-shaped transistor. Its size is scaled down by many orders of magnitude. A transistor is a digital switch. It is the fundamental building block of IC chips. It is a 3-terminal device, source, drain, and gate. For certain values of gate voltage, current can flow between source and drain. For other conditions of the gate voltage, almost no current can flow between source and drain. So if we use a water tube analogy, gate is like a valve that controls the flow of current from source to the drain. That is why we see transistor is like a digital switch. It may sound like a very simple design. One transistor cannot accomplish too much other than switching between 0 and 1. But when you have billions of transistors, many amazing applications can be enabled, from autonomous driving, smartphone to Internet of Things. So we have a strong motivation to make transistors smaller and smaller, because that means we can have more transistors per unit area in an IC chip, and more transistors bring more functionality and more powerful applications. However, at this stage, making transistors smaller is becoming more and more challenging. That is because below certain scale, transistors would suffer from something called short channel effects, which are fundamental challenges faced by the semiconductor manufacturing industry. As you can see, both drain and gate bias have an impact on the behavior of carriers in the channel. The drain establishes a lateral electrostatic impact on the channel, and the gate establishes a vertical electrostatic impact on the channel. Ideally, we want the gate to always hold a tight control over the channel. But when the channel is scaled down to a few nanometers, the drain gets so close to the source that it could dictate the carrier's electrostatistics in the channel. In other words, the gate will lose control over the channel. Here shows the energy band diagram of a transistor when short channel effects occur. Again, if we use the water analogy, that means the gate as a valve is no longer working. You will always have a leakage of current between the source and drain, no matter how tightly you turn the valve. How to solve this problem? Well, a rule of thumb is that the lateral and the vertical scaling of a transistor should be done simultaneously. When you make the transistor channel shorter, you have to make sure that the semiconductor channel and the dielectric layer also get thinner and thinner. Intuitively, that will allow the gate physically get closer to the channel and maintain a tight electrostatic control. And that turns out very challenging to achieve, especially nowadays. We have already pushed the size of a transistor to nanoscale. The semiconductor channel thickness also get down to nanoscale. And silicon is a three-dimensional material. Its surface always have lots of dangling bonds which introduce carrier scattering. Its surface is very different from its bulk. As shown in this figure, when you scale the thickness of silicon down to a few nanometer, the carrier mobility of silicon will drop exponentially because of the surface effect. In other words, down to a few nanometer, silicon will no longer be the same silicon as we know before. We would need new semiconductors. And it turns out that in this nanometer regime, there exists a group of semiconductors that are only atom thick and can outperform silicon in terms of mobility. They hold great prospects in further extending the scaling of transistors beyond silicon. We also call these atom-thick semiconductors two-dimensional semiconductors or 2D semiconductors. They represent the ultimate scaling of semiconductors and electronics. MoS₂ or molybdenum disulfide is such an example. It has very strong in-plane covalent bonds. However, different layers only couple with each other through very weak van der Waals bonds. This makes it possible to exfoliate one individual atomic layer. This strong in-plane covalent bonding makes it mechanically robust, even though they only have few atomic layers. Recently, we built an ultra-scaled transistor with bilayer MoS₂ as channel material, and we developed a new fabrication technique to scale the channel length down to about 5 nanometer. And here shows the performance of such a 5 nanometer channel length transistor. Thanks to the atom-thick semiconductor channel, we can get an on-off ratio around 10 to the power of 6 and 10 to the power of 7, even when the channel length is scaled down to about 5 nanometer. And most importantly, we can have the off current around 1 picoampere per micrometer. That is very low as a sub 10 nanometer transistor. Low off current means low static power consumption. To build a circuit, we need not just the semiconductors, we also need metals and insulators. Fortunately, two-dimensional materials are more than semiconductors. There is a family of 2D materials that cover a full spectrum of electronic components, from metallic graphene, semiconducting transition metal that are cognized, to insulating boron nitride. Basically, they provide all the necessary components to build flexible electronics. Take graphene as an example. It is a single layer of carbon with thickness of 3.4 angstrom. To give you a scale bar, it is similar to the spacing between two base pairs of a DNA helix. With only one atom thick, its Young's modulus is 5 times higher than steel, mobility 100 times higher than silicon. Many new physics appear due to the quantum confinement in the z direction. A very unique property of 2D materials is that they do not have dangling bonds. It means that we can do straightforward heterogeneous integration of multifunctional layers. We can assemble these one atom thick materials in a layer by layer fashion. You can do it in whatever combination and order you want. It's just like building Lego squares. It is hard to think of any other materials that you can do it at the atomic precision and in a large scale and low cost manner. To make a real impact, we need to think from a system level perspective. Any system level application requires 4 basic building blocks: energy, computation, communication, and sensing. And it is important for us to know how to engineer these atom-thick materials and understand their basic science. So I will first give you one example of material engineering, then focus on electronic applications of 2D materials. Doping is important for building almost any circuit, as it allows us to tune the conductivity of semiconductors. For 3D materials, we can change their doping level through ion implantation. However, for 2D materials, we only have one atom thick. ion implantation will not work because that will fundamentally change their intrinsic structure. Therefore, it is important to develop non-invasive doping technology. Take graphene as an example. By introducing doping, we can tune its Fermi level. And many of its key properties are a function of Fermi level, such as conductivity, Seebeck coefficient, and the plasmonic frequency. This tunability is a very unique feature of graphene. If we can find a way to effectively tune its Fermi level, many optoelectronic applications can be enabled. Based on DFT calculations, we found that chlorine in the group 7A of periodic table is very promising to introduce strong doping in graphene because of their relatively large electron activity. At the same time, the underlying graphene can largely maintain its sp2 planar structure. Chlorine can introduce the right amount of interaction with graphene, and that is the key to get non-invasive doping. We use an electron cyclotron resonance plasma chamber to generate chlorine plasma and dope graphene. The key is to generate a chlorine plasma with the lowest possible kinetic energy by fine-tuning an RF bias applied to the substrate. After optimization, we quantify the carrier density change in graphene. The whole carrier density in graphene was enhanced by about 3 times on average. Hall effect measurements and a statistics study also confirmed that the high mobility of CVD-grown graphene can be largely maintained after chlorination. In order to confirm this is a non-invasive process and understand the bonding nature behind this process, we also did X-ray spectroscopy to characterize the chlorinated graphene samples. First, from the XPS, we quantified the surface coverage of chlorine to be about 45%. Very surprisingly, such a large amount of coverage does not disturb graphene's intrinsic structures and properties. TEM diffraction pattern can also clearly reveal this. We also did a near-edge X-ray absorption fine structure spectroscopy, which allows tuning the polarization of X-ray beam and probing the fine structure of the surface states of chlorinated graphene. We identified a very strong polarization dependence in the carbon pi bond and carbon sigma bond. And next to the carbon-carbon pi bond, we see a clear peak corresponding to the carbon-chlorine bonds. It shows a positive shift in resonance peak of 0.8 eV, which is significant. It explains the strong hole doping effect. Angle dependence analysis also reveals a lot of new features that are different from conventional 3D materials. Most importantly, we also see that the sp2 core hole acetone peak does not change much after chlorination. That is a fingerprint of long-range periodicity of graphene. You can only see it in very high quality samples. So all the characterization results confirms that the chlorination process is both effective and non-invasive. That is one example of how we developed a fundamental processing technology, doping, using graphene as a case study. What about the applications? Here I will mainly focus on the energy part. 2D materials make it possible to build electronics that are ultra-thin and flexible and can be integrated with almost everything. As sensors and transistors are transforming into flexible forms, the energy solution turns out a lot more challenging to be transformed into flexible forms. In particular, we need new power solutions for the vision of ubiquitous electronics, and we want them to be flexible and ubiquitous. The current technologies such as batteries, solar cells, biofuel, etc., are difficult to fulfill these requirements. For example, batteries are often bulky and require regular replacement. Solar cells won't work for devices that are embedded in large buildings. So what energy sources can we take use of? Well, one option can be the radio frequency energy in the air. We are surrounded by an abundant source of wireless RF energy in the so-called SM band. Most of our daily electronics, such as Wi-Fi and cellular phones, work in this regime. 2D semiconductors provide an opportunity to build such a fully flexible and integrated RF energy harvester, which is also called Rectenna. It is essentially a rectifying antenna. The key is to minimize the RC time constant of the rectifier, which is a key component of the rectenna. This challenge can be solved by taking advantage of the unique phase property of MoS₂, which is an atom-thick semiconductor. MoS₂ can exhibit two phases, one 2H semiconducting phase and 1T prime metallic phase. Such a phase engineering provides us a new degree of freedom to play with and a new design space. We developed a self-aligned lateral semiconducting metallic phase junction of MoS₂ and built a Schottky diode in which the boundary of the Schottky junction perfectly aligned with the boundary of the MoS₂ phase junction. This structure allows a simultaneous reduction in series resistance and parasitic capacitance. Here shows how we model the circuit and the DC characterization of the MoS₂ phase junction diode. It shows a high intrinsic responsivity of 4.7 ampere per watt at 0 external bias. We also characterize the high frequency performance of the device by measuring its S parameters using a vector network analyzer. A very important parameter for the device speed is the junction capacitance. Near 0 bias operation regime, the junction capacitance of our device is below 10 femtofarad, which is roughly 10 times smaller than alternative technologies. From this, we can calculate the cutoff frequency of the MoS₂ Schottky diode. At 0 bias, it is about 10 gigahertz. So we built a demonstration circuitry to experimentally measure this device. In this demo, we use two Wi-Fi band antenna, one as transmitter, the other one as receiver. The receiver antenna collects the EM wave and converts it into AC current. The AC current is rectified by the MoS₂ diode and power a load at the output. Based on the -3 dB point definition, the cutoff frequency of this device is 10 gigahertz. It is high enough to cover both Wi-Fi and a cellular band. We also measure its output voltage as a function of input power at 4 different frequencies from 2.4 gigahertz to 15 gigahertz. Here is just one example of what can be achieved by taking advantage of the unique properties of two-dimensional semiconductors. Such a fully flexible and integrated wireless energy harvester could potentially be very useful for many IoT applications. Besides energy, 2D materials also have various applications in the computation, communication, and sensing domains. For the sake of time, I will skip the details. So far, I have shown you some examples of new possibilities that can be enabled by 2D materials, from material engineering, technology development, to the nano device fabrication and integration. This is a very special platform to build novel electronics. As we push electronic materials to the atomic limit, there are many different opportunities for us to explore. It is promising to further extend Moore's law and continue the semiconductor scaling. It also offers new opportunities in the more than more perspective because we have a diverse group of 2D materials. Many of these materials have unique and tunable properties that allow us to explore new device concepts and new physics. Last, I want to thank my students in my group at Carnegie Mellon University and all my collaborators from academia to industry. And thank you all for your attention.